Hello great minds! Welcome to Scholar's Edge tutorial. In this video, we would be looking at the subject, chemistry. Topic, atomic structure. Before going into atomic structure, let's first of all find out the meaning of an atom. An atom is the smallest unit of a substance that still has the properties of that substance. It's like a tiny Lego brick that can't be broken down further. Think of it like a tiny package. An atom is a tiny package that contains protons, which are positively charged, neutrons, which has no charge, electrons, which are negatively charged. Atoms are the building blocks of everything around us, from the air we breathe to the stars in the sky. They're the tiny units that makes up all matter. Here is a simple analogy. Atoms are like individual Lego bricks. Just as Lego bricks can be connected to form different structures, atoms can be combined to form different substances, like water or carbon dioxide. Now we've known what an atom is, let's find out the meaning of atomic structure. Atomic structure is the arrangement of tiny particles, called protons, neutrons, and electrons, that makes up an atom. Recall that an atom is the smallest unit of a substance, and it's been made up of protons, neutrons, and electrons. So the arrangement of this protons, neutrons, and electrons in an atom is referred to as atomic structure. In simple terms, protons are positively charged particles that live in the center of the atom. Neutrons have no charge and live with protons in the center. Electrons are negatively charged particles that orbit around the center. That's the basic idea of atomic structure. In other words, atomic structure describes the internal structure of an atom, protons, neutrons, electrons. How atoms are arranged in reaction to each other in a substance. The type and number of chemical bond between atoms. So you can say that atomic structure is the blueprint or layout of how atoms are organized in a substance, including the connection between them. Here's a simple example. In a water molecule, H2O, the atomic structure shows two hydrogen atoms bonded to a single oxygen atom. The number of protons, neutrons, and electrons in each hydrogen and oxygen atom. The type of chemical bond between the atoms. Having understood the concept of atomic structure, let's move further to electron configuration. Imagine a big house with many rooms. These rooms are called energy levels. Each room can hold a specific number of people. These people are called electrons. Electron configuration is like assigning people, electrons, to rooms, energy levels, in the house, atom. It shows how electrons are arranged in an atom. Think of it like a party. Each room, energy level, has a limited number of seats, electron capacity. Guests, electrons, arrive and fill the rooms in a specific order. Once a room is full, guests move to the next available room, energy level. Let's describe the energy levels, rooms. The first room, energy level, is closest to the nucleus, center of the atom. Each subsequent room is farther away from the nucleus. Rooms can hold different numbers of guests, electrons. Let's find out the rules guiding electron configuration. Fill the lowest energy rooms, energy level, first. Fill rooms with the lowest number of guests, electrons, before moving to the next room. Follow specific rules to ensure guest, electrons, are arranged correctly, like the Pauli exclusion principle, which states that no two electrons in an atom can be exactly the same. Think of this principle like a room with many chairs. Each chair represents a unique spot where an electron can sit. If one electron is already sitting on a chair, no other electron can sit on that exact chair. Electrons have four characteristics, which are energy level, how high or low they are. Shape, what kind of orbital they occupy. Orientation, which direction they face. Spin, whether they rotate clockwise or counterclockwise. Pauli exclusion principle states that no two electrons can have the same combination of these four characteristics. This means each electron must be unique, like a snowflake. There are two ways of writing electronic configuration. meaning two ways of assigning electrons to rooms. The first method is the shell notation, or energy level notation. Imagine a series of concentric circles, shells, around the nucleus of an atom. Each shell represents an energy level which we are referring to as room. Let's describe the shell structure. The first shell is closest to the nucleus. Each subsequent shell is farther away. Shells have specific capacities, number of electrons they can hold, just like the rooms have specific people it can contain. Let's also look at each shell capacity. The first shell, which is the K shell, can carry a maximum of 2 electrons. The second shell, which is the L shell, can carry a maximum of 8 electrons. The third shell, which is the M shell, can carry a maximum of 18 electrons. The fourth shell, which is the N shell, can carry a maximum of 32 electrons.
To find the number of electrons each shell can carry, we use the formula 2n superscript 2, where n equals number of shell. So let's take for example we want to find out how many electrons the fifth shell can carry. We use our formula 2n superscript 2, and our n equals 5. 5 superscript 2 equals 25. We are left with 2 by 25, which will give us 50. That's to say the fifth shell can carry a maximum of 50 electrons. Let's learn how to write electron configuration using shells. Write the electron configuration for the following elements using shells. 1. X5 2. Z16 3. Y32. The elements given are unidentified elements, so let's write their electronic configuration using shells. For the first element X5, first thing you need to do when writing an electron configuration using shells is to draw your nucleus which contains the proton and neutron. Next thing is to draw a circle. We refer to this circle as shell. So we have our first shell. Recall that the first shell can carry a maximum of 2 electrons only. So we assign the first shell 2 electrons. We were given 5 electrons from the question, so we are left with just 3 electrons after assigning 2 to the first shell. Next we do is to draw another shell, which is the second shell. Recall that the second shell can carry a maximum of 8 electrons only, but we are left with just 3 electrons, so we assign it to the second shell. And now we are left with nothing. So writing out our electron configuration, the first shell had 2 electrons, we write it out, the second shell had 3 electrons, we also write it out, and that's our electron configuration. It's that simple. Moving over to number 2. Z16. So the first thing we do is draw our nucleus, next is our first shell which we assign 2 electrons since that's the maximum it can carry. We draw the second shell and assign it 8 electrons since that's the maximum it can also carry. Don't forget we were given 16 electrons from the question. So we are left with just 6 electrons. We draw a third shell which can carry a maximum of 18 electrons, but since we're left with just 6 electrons, we assign it to the third shell leaving us with nothing. So let's write the electron configuration. The first shell had 2 electrons, we write it out, the second shell had 8 electrons, we write it out, the third shell had 6 electrons, we write it out, and that's our electron configuration. Lastly number 3. Y32. So first we draw our nucleus, then we draw the first shell and assign it 2 electrons, next is the second shell. We assign it 8 electrons, we also draw the third shell and assign it 18 electrons, since that's the maximum it can carry. Don't forget we were given 32 electrons in the question. So now we're left with just 4 electrons, so we draw the fourth shell and assign it 4 electrons since that's what's left. Writing out the electron configuration, the first shell had 2 electrons, so we write it out, the second shell had 8 electrons, we write it out, the third shell had 18 electrons, we also write it out, and the fourth shell had 4 electrons, we write it out. And that's the electron configuration. Having understood writing of electron configuration using shells, we move over to the second method. The second method of writing electronic configuration is orbital notation or subshell notation. This method groups electrons by their orbital or subshell. It's written in a format that shows the orbital type S, P, D, F, and the number of electrons in each orbital. Imagine a house with rooms, orbitals, where electrons live. S orbitals are like a single bedroom, one room, where 2 electrons can sleep. P orbitals are like a 3-bedroom apartment, 3 rooms, where 6 electrons can sleep. D orbitals are like a 5-bedroom house, 5 rooms, where 10 electrons can sleep. F orbitals are like a big mansion, 7 rooms, where 14 electrons can sleep. Each room, orbitals, has a specific energy level. Electrons fill the rooms, orbitals, in a specific order. When a room, orbital, is full, electrons move to the next available room. Shapes of orbitals. S orbitals are like a sphere, a ball. P orbitals are like a dumbbell, a weightlifter's weight. D orbitals are like a 4-leaf clover. F orbital are like a complex multi-lobed shape. Arrangements of orbitals. Orbitals are arranged in an SPDF format and are attached to numbers. An easy way to understand how orbitals are arranged is, first you write out the s orbitals attached to numbers in a vertical format. So we have 1s, 2s, 3s, 4s, 5s, sixs, and so on. Next is to write out the p orbitals attached to numbers in a vertical format starting from number 2. So we have 2p, 3p, 4p, 5p, 6p, and so on. We do the same for d orbital starting from number 3. So we have 3d, 4d, 5d, 6d. And lastly for f orbital, we do same thing starting from number 4. So we have 4f, 5f, 6f and so on. Now how do we determine which orbital comes first before another? This is how it is done. In determining which orbital comes first before another, we draw a diagonal arrow to the left starting from 1s. We draw a diagonal arrow to the left, starting from 1s. Having done this, we pick each orbital according to the arrow. So the first orbital is the 1s orbital, followed by 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on. Note that this list only goes up to 5p orbital, but there are more orbitals beyond that. So let's write an electronic configuration using orbitals. Write the electron configuration for the following elements using orbitals and determine how many electrons are unpaired. 1, x5. 2, z10. 3, y16. So for our number 1, x5. The first thing we have to do is to write out the first orbital, which is 1s, and recall that the s orbital can carry a maximum of 2 electrons only. So we assign it 2 electrons. After the 1s electron, comes 2s. We also assign it 2 electrons, and now we're left with just 1 electron. So we write the next orbital after the 2s orbital, which is 2p, and we assign it the remaining 1 electron. Recall that the p orbital can carry a maximum of 6 electrons. So that's our electron configuration. So simple, right? Now the question said we should determine how many electrons are unpaired. So for the first orbital 1s superscript 2 we draw a box. Recall that we said that the p orbital is like a 1-bedroom in which only 2 electrons can sleep. So this box is the 1 room, and we assign it the 2 electrons in 1s superscript 2 to sleep there. Next is the 2s superscript 2. We do the same thing we did for 1s superscript 2 for it since they're under the s orbital and carrying the same number of electrons. Next is the 2p superscript 1 orbital. Recall that we said the p orbital is like a 3-bedroom that can carry a maximum of 6 electrons. So we draw 3 boxes representing this rooms, and we assign just 1 electron to the first box since 2p superscript 1 was assigned only 1 electron. So looking at what we just did, we can say only 1 electron is unpaired, which is the first one in 2p superscript 1 orbitals. Moving over to number 2. Z10. We write out our first orbital 1s, and assign it 2 electrons, next is 2s, and also assign it 2 electrons. According to the question, we were given 10 electrons but we have just 6 left. So we write out the 2p orbital and assign it the remaining 6 electrons since that's the maximum it can carry. So let's determine how many electrons are unpaired. So first we do is to draw our boxes for each of the orbitals, after that we input the electrons assigned to each of them. So for 1s superscript 2, we input 2 electrons into the box, we do same for 2s superscript 2, and lastly for the 2p orbital. We input 1 electron to each of the 3 boxes starting from the first box, after which we are left with just 3 electrons. So we repeat same process, and we are left with nothing. So looking at everything, we can see that all the electrons are paired, there are no unpaired electrons. Lastly, number 3. Y16. So we have our first orbital as 1s, we assign it 2 electrons, we do same for 2s, and for 2p orbital, we assign it 6 electrons. Now we are left with 6 electrons. So we write the next orbital after 2p orbital, which is 3s, and we assign it 2 electrons since the s orbital can only carry a maximum of 2 electrons. And now we are left with 4 electrons, so we write out the next orbital, which is 3p, and we assign it the remaining 4 electron, and that's our electron configuration. Determining the number of unpaired electrons, we draw our boxes for each of the orbitals, then we input our electrons. First is the 1s superscript 2 orbital, we input 2 electrons since that's what it was assigned, we do same for the 2s superscript 2 orbital, and for the 2p orbital, we input 6 electrons starting from the first one. After making sure each of the boxes in the 2p orbital has gotten 1 electron each, we input the remaining 3 electrons. Next is the 3s superscript 2 orbital, we input 2 electrons into its box since that's the maximum it can carry, and that's how many it was assigned. And lastly, for the 3p orbitals, we input 1 electron to each of the 3 boxes first starting from the first box, and we are left with just 1 electron, so we assign it to the first box. Looking at everything, we can say that only 2 electrons are unpaired, which are the last 2 electrons. With the knowledge we've gotten on atomic structure, let's solve some questions. Which of the following subatomic particles has a positive charge? A. Electron. B. Proton. C. Neutron. D. Photo. The correct answer is option B, proton. Recall that proton is a positively charged particle found on the nucleus of an atom. Question number 2. The number of electrons in an atom of an element is equal to the A. Atomic number. B. Mass number. C. Atomic mass. D. Valency. The correct answer is option A, atomic number. Atomic number is the number of protons in the nucleus center of an atom. Think of it like a unique ID card for each element. Just like how your ID card has a unique number that identifies you, an atom's atomic number identifies what element it is. If an atom has 6 protons on its nucleus, its atomic number is 6, and it's a carbon atom. If an atom has 8 protons, its atomic number is 8, and it's an oxygen atom. However, atomic number equals electron number only for neutral atoms. Question number 3. Which of the following orbitals is spherical in shape? A. S orbital. B. P orbital. C. D orbital. D. F orbital. The correct answer is option A, S orbital. S orbitals are spherical in shape. Question number 4. The maximum number of electrons that can occupy the p orbital is A. 2. B. 6. C. 10. D. 14. The correct answer is option B, 6. The p orbital can carry a maximum of 6 electrons. Recall the illustration that was given, that the p orbital is a 3-bedroom that can carry 6 people, electrons. Question number 5. The electron configuration of an atom with 12 electrons is A. 1s superscript 2, 2s superscript 2, 2p, 3s superscript 2. B. 1s superscript 2, 2s superscript 2, 2p, 3p superscript 2. C. 1s superscript 2, 2s superscript 2, 2p, 3s superscript 2, 3p superscript 2. D. 1s superscript 2, 2s superscript 2, 2p, 3s superscript 2, 3p. The correct answer is option A, 1s superscript 2, 2s superscript 2, 2p, 3s superscript 2. Question number 6. The outermost energy level of an atom is called the A. Valence shell, B. Inner shell, C. Electron bond, D. Nucleus. The correct answer is option A. Valence shell. Valence shell is the outermost layer of electrons in an atom. Think of it like a house. The nucleus, protons and neutrons, is the living room, center of the house. The electrons are like people living in the house. The valence shell is the outermost room where the people, electrons, interact with the outside world. In other words, the valence shell is the outermost energy level of an atom, where the electrons that participate in chemical reactions are located. It's like the interaction zone where atoms meet and greet each other. Lastly, question number 7. The number of electrons in the outermost energy level of an atom determines its A. Atomic number, B. Mass number, C. Chemical properties, D. Physical properties. The correct answer is option C. Chemical properties. Recall that the valence shell is the outermost energy level of an atom, where electrons that participate in chemical reactions are located. So the number of electrons in the valence shell determines the chemical properties. That's all on atomic structure. I hope you have learned something from this video. Don't forget to subscribe, like and share. Scholar's Edge tutorial is here to make your difficult topics very simple. Thanks for watching.